So this talk is going to be, is going to be very different than the previous talks. And I'm also the experimentalist. So this work I have done when I was at Stanford, and most of the experiments are done at SLAC synchrotron radiation. So when we are talking about quantum dots, so quantum dots, we know that they are the semiconducting nanoparticles which shows quantum confinement, correct? And we can make different type of heterostructures within this quantum dot so that they exhibit different optical properties. This, the materials, these materials came up probably 2 decades ago roughly from when people started researching. And we can easily tune the composition, the band gap with composition or with the size. And these materials are useful, or people are using or exploring these materials for light emitting diodes or for solar cell photovoltaic purposes in different cases. Okay, so when we are talking about quantum dots, then most of the time we are saying that the inorganic part. But in chemical synthesis process, there is always these organic molecules which we call the passivating molecules. They're around this inorganic core, and these passivating molecules basically alter a lot of properties. So basically they bring a new properties along with this inorganic core material. So they control these passivating molecules, they control the size and size distribution of this when we are synthesizing this inorganic core. They can modify the anisotropy as well as they help in stabilization. So basically we can think of, say, this is the quantum dot, the ligand part, and this is the quantum dot, and these interactions basically control a lot of these properties. And these are some of these examples. So for example, if you take gold nanoparticle, and this is of huge size distribution, and if you treat with some of this thiol molecule, then from here it goes to a very perfect size distribution. And these are, due to this interaction between this ligand and the quantum dot, these are formed in nanosheets kind of structure. And of course, by controlling this ligand, you choose whatever the type of the ligands, you can make this inorganic core either soluble in polar solvent or non-polar solvent. Okay. So, but there are some issues with these colloidal quantum dot solids. So first of all, if we try to use these quantum dots in some electronic structure, electronic system, these quantum dots has to be coupled with each other. But we always have these ligand molecules which actually helps in some way, also they cause some problem. So this is one 18 carbon chain long molecule which is commonly used during the synthesis. This is called oleic acid. And the charge transport of this colloidal solid, this colloidal quantum dot solid, it depends on, of course, first of all, it depends on how far these quantum dots are separated. That means the length of these ligand molecules. And the size distribution of these quantum dots, the surface chemistry as well as stoichiometry, and the morphological order. So in this case, I have shown these particles as spherical, but in several cases they have faceted structure. And if there is any morphological order, does that affect this charge transport of this colloidal quantum dot solid? So that is what we are trying to see from this, we'll try to explore in this talk. So this is the transmission electron microscope image. So we take this quantum dot, put it on a grid, TEM grid, and then what we are looking here is basically one monolayer of quantum dots. What we find here that these quantum dots are organized beautifully. It's not exactly hexagonal, but it's a distorted hexagonal pattern. And from here, we can also find out what is the interparticle distance from this TEM image. And the interparticle distance is around 5.5 nanometer. And that is something, so that should be the radius of the nanoparticle plus 2 times the length of the ligand molecules. So if we calculate this one, we find that it suggests that these quantum dots and the ligands, they're kind of interpenetrating inside, and that's how they form this type of structure. But TEM is just one, it gives information about one single monolayer. So we want to look at what happens in the 3-dimensional. So what we did is Grazing incidence small angle is X-ray scattering basically. And this one we did on the 3D solid to get us to know what is the structure of this solid. So this is the experimental result of this GISAXS pattern. And if we can label this one, we find that the whole quantum dot solids, they're forming in a BCC superlattice. So in this BCC lattice, each of these lattice points are the individual quantum dots. And we also did some grazing. So this is, first of all, this is interesting that why these molecules or these quantum dots are forming in this superlattice. And then you can find the interparticle distance from here, which matches very well with this TEM experiment what we have got. Now, what we also did is looked at the grazing incidence X-ray diffraction. So basically, in this case, now we are looking at, earlier we had looked at only at this small space, this region. Now we are looking at much larger Q. That means we are looking at the atomic planes of this quantum dot. And in this case, we find that this is a lead sulfide. It forms in rock salt, NaCl crystal structure. We find that diffraction, this peak 111 or 220 or even 022, they are oriented in some particular way. So it suggests if we decipher this structure, then we find that this is how the quantum dots are oriented when we are treating with this oleic acid. Okay, so the overall three-dimensional picture is that this is the plane of this BCC superlattice which is perpendicular to the substrate, and the individual quantum dots, they are oriented such that 011 plane is perpendicular to the substrate. Okay, good. So this is what happens probably because this oleic acid, these long molecules, they interact with each other, and that's where it goes to this particular BCC superlattice structure. Now, when we try to use this oleic acid passivated molecules, as this is an 18 carbon chain long molecule, so the flames are almost insulating, so we cannot work with that for any electronic purpose. So we change those big molecules with some smaller molecules, let's say mercaptopropanoic acid, which is 3 carbon chain long molecule. And all this we are doing in the solid state. So first we have this lead sulfide, we put it on the wafer, then we have this solid flame. So the previous results what I have shown is from this flame. Now what we are doing this ligand in the thin film, in the quantum dot solids we are applying, and then we are just spin coating and washing this up. So let's see what happens with this effect of this mercaptopropanoic acid or these small molecules. So we find, so this was the earlier structure without treatment of these small molecules. Now when we start treating with different concentration, then we find that there is along this QZ axis, that means which is vertical to the plane of the substrate, we find an asymmetry which is building up. And then eventually it forms a heterogeneous or means a broad peak. That means it goes to a kind of a random type structure with an average interparticle distance. So this tells that from BCC it goes to some sort of phase transition to this type of structure, and then it goes to ultimately to a disordered system. So we deciphered, let's not go to the much technical details. So from looking at one particular peak, we can find out that from BCC structure, it goes to a body-centered tetragonal, and then it goes to a distorted structure, and finally to a disordered superlattice. So and we also did this grazing incidence X-ray diffraction, where we find that now this earlier the 111 peak was just here. When we treat with some higher concentration of this ligand or the small molecules, then 111 peak is now coming perpendicular to the substrate. That means these particles, so if I compare with respect to so when we are in this solid thin film, when we are treating with these small molecules, then all the particles, they're kind of rotating within this thin film. And these planes are becoming parallel to each other. Whereas earlier this was the kind of the structure of the individual quantum dot in this quantum dot solid, as in this case now the facets are kind of oriented. Okay, so this is the overall picture what we have got. In this case, so this is with the big molecules, oleic acid, that we find a BCC superlattice with 011 plane perpendicular to the substrate. Whereas when we did treat with the small molecules, then it kind of goes to a BCT because this axis basically decreases, and then each of the facets of these quantum dots, they also kind of they orient. And in this case, so why does this happen, this particular phenomena, why do we observe this? So in this case, I only have the idea of, so basically this molecule, oleic acid, it's a COO, so carboxylic acid group at the end, which binds to this lead of this lead sulfide quantum dot. Now at two facets, if we look cross this lead sulfide, if we look at 100 phase or 111, the distance between two lead atoms are different. And the oleic acid, that's why they bind in different strength. So when we treat with this the molecule, it first represents from 100 facets. So that's the orange facets. Now what happens that this is what our proposition is, that to accommodate both these long molecules and the small molecules within this solid, the whole quantum dots within the solids, all the quantum dots, they're kind of rotating. And thus we are getting this type of structure. So why this is important at all to have this type of structure? So we are looking, so the substrate was at the bottom pair. So this is always, I'm showing the particle to the substrate. In this case, if we're looking, say for example, when we are interested in quantum dot, the charge transport in this system, then if the two facets of these quantum dots are parallel to each other, then of course the charge transport through this direction is going to be much better compared to in this direction. So people are now looking for these coupled quantum dot systems so that we can retain this quantum confinement, but still have a much higher charge transport in these solids. So what we have learned from this work, that these long chain molecules, they make these quantum dots in BCC superlattice with a particular 011 direction perpendicular to the substrate. And these small molecules, they change this BCC lattice to BCT, and then finally it goes to disordered system. And this happens most likely because of these different interactions between the thiol molecule, that's the small molecule functional group, and the carboxylic acid, which is the big molecule functional group. And that's what it leads to the interactions between them at different facets are different. That leads to this change in the crystal structure, superlattice structure. So the take-home message is ligand quantum dot interaction and the ligand length or ligand-ligand interactions, they are the one which are playing critical role in this type of superlattice. So it can be helped in, means the implication from here is that the role of concentration of these passivity molecules are important, as well as the charge transport can be controlled via the orientation of these quantum dots in the solids. Thank you. So I did this work with Axel, Stacy, and from SSRL, Christopher, they helped. Thank you for your attention.
How thick are these layers?
So this layer are around 30 nanometer thick.
Can you make them extremely thin, like a couple of layers, or?
So one monolayer, it can be done. It can be done. The only problem when you go very thin layer, then the uniformity of this flame is going to be a little bit problematic. But it is possible to do it.
And is it known that it still remains?
I have not done that one. I have not studied that. I have also not seen any report on that one. So I cannot really, in this case, what will happen that if we are, these molecules, even these quantum dots, even if they orient, that might help in the charge transport, but these ligand molecules are also kind of a barrier because they are kind of the insulating molecules, right? So that prevents the overall charge mobility to some extent.
So what is the properties of these individual dots? I mean, can they become magnetic?
These are all
non-magnetic, but are there like magnetic dots like this?
I think for some of these magnetic nanoparticles, people have, there the ordering is much more compact. For example, how do you say, iron oxide or Fe3O4 nanoparticle, ferric oxide. People have seen this type of ordering, and they have assigned it to this magnetic force, but it's, yeah. Does that answer your question? Or so as we are making these solids, the band gap decreases a little bit from individual particle in solution, but otherwise when we are treating with these molecules, small molecules, we do not really observe any change in the optical absorption.